Hello guys, welcome to my channel BinChem. Today we are going to see a pericyclic reaction. In this electrocyclic method only we are going to see in brief. This will be helpful for all exams. Okay, see the pericyclic reactions we can segregate into two types of reaction. One is electrocyclic reaction, one is cycloaddition reaction. What is the difference between these two? Electrocyclic reaction takes place in one molecule itself it takes place, but in a cycloaddition reaction takes place between the two molecules. Then only you will get a cyclic product. Okay, it may be a ring closed cyclic product. That is the best example is diels-alder reaction. In the electrocyclic reaction, it may leads to a ring closed product or a ring opening product. Both will takes place. Okay, so we are going to see here the electrocyclic reactions very briefly. Here the electrocyclic reaction means, see, as I said earlier, this is within it takes place in a molecule. Okay, within a molecule it takes place the rearrangement. So here the new sigma bond is formed. See here, this will come here and this is going here, this is going here. So the new sigma bond is formed over here. This is the ring closure. And see here the electrocyclic ring opening. Here this is coming, this bond is come to this side, and this bond is breaking and it goes to that side. So cleavage takes place in the sigma bond. So it leads to a ring opening. These two are electrocyclic reaction. If it goes to the cyclic, that is cycloaddition, that is it gives a cyclic product. This is the best example for a diels-alder reaction. Two compounds is there. See, butadiene and alkene, that is ethylene. Both will react and it form a ring closed reaction. This bond will go here and this bond will be here and this bond will be over here. So it will be like a hexene. Okay. And a new sigma bond is formed over here and new sigma bond is formed over here. This new pi bond is formed. Here the single bond, it becomes pi bond. This is the cycloaddition. Okay. The next, see in this reaction, okay, the stereochemistry is very important in the electrocyclic reaction. All the electrocyclic reactions are completely stereospecific. See, this is also 1,3,5-triene. This 1,3,5-triene EE compound gives only cis product, not the trans product. See here, cis product is formed, not the trans product. And if it is cyclic compound of a cis product on thermal condition, it gives E and Z configuration and not EE configuration. Why is it so? See, all the electrocyclic reactions are half reversible reaction also. So it will reverse to this product reactant also. See, on this condition, if you go to the thermal as well as the photochemical reactions, you will get the product of a trans as well as the cis. Why is it so? What is happening here on the photochemical reaction on thermal conditions? We know already it's a thermal condition. This is happening, this rotation, everything we know, but why is it so? We will see in the next slide, which determine the reactions. The two things which is important to determine the reaction, that is number of pi bond and the conditions which is taking place in the reactions, whether it is a thermal condition or the photochemical condition. These two are very important. If you take ethylene, in this compound you will get only one pi bond. If you see 1,3-butadiene, in this compound we will get 2 pi bonds. If you see 1,3,5-hexatriene, 3 pi bonds are there. Okay, what is there in that? Because of that, what is happening here? See, in this orbital symmetry is very important in this case. When it is in a like phase of orbital, will overlap and it gives proceed to electrocyclic reaction, because it is a symmetry allowed overlapping. When it is in opposite phase, this is not allowed. This is a symmetry forbidden overlap. So in this type of reaction, this electrocyclic reaction will not take place. So what we need to do with this type of opposite phases are there? In that case, we need to change the rotation of this and we need to make it as a symmetry overlapping. See, if this is the same case, both will get in a clockwise and anti-clockwise rotation. This rotation, that is this rotation, the overlap will be, the symmetry overlap will take place, the new sigma bond will form. But if it is in the opposite phase, so the rotation will be in the clockwise rotation. Both will take place in the clockwise direction, so that we will get a conrotation, then we will get a new sigma bond. That's why this orbital symmetry is very important in this case of the disrotation and conrotation. If you see ethylene, it's only one double bond is there. The energy levels goes on like this. So how many carbon atoms are there? That many levels will be there. So 2 levels are there, 2 carbon atoms, 2 levels are there. So 2 electrons are there, 2 electrons are filled in the bonding molecular orbital. This is a pi bonding molecular orbital, this is pi star anti-bonding molecular orbital. Only p orbital we are seeing here. In this case, always the pi bonding molecular orbital, the first level will be always in the same phase. It will get overlap and will get like this. If it is an opposite phase, the overlap will not take place. Here the node will form. Okay, this is the energy levels of the p atomic orbitals. We'll see for the next compound, that is 1,3-butadiene, that the 4 electrons are there, that is 2 pi bonds are there. Okay, how many carbon atoms? 4 carbon atoms. So 4 energy levels are there. According to the from the down to the top, the energy level will get increases. See, in this case, the first level always the same phase will be there, same phase of orbitals will be there, so it will get overlap. Okay, and in the second phase it will be different will be there. Whenever the difference is there, the overlap will not happen, that node will form. And in the third phase 2 nodes will form, and in the fourth phase 3 nodes will form. According to the level, one less node will get. The first phase, the first level 0 node, and second 1, and the third 2 node, and in the fourth 3 nodes will be there. Okay, see here how many electrons? 4 electrons are there. The 2 electrons in the first level and there are another 2 electrons in the second level. This we call it as the HOMO. What is that? Highly occupied molecular orbital. This we call it as a LUMO. What is that? Lowest unoccupied molecular orbital. Okay. And this is the normal ground state level. After applying that photochemical, that is H nu, the photochemical reaction, what is happening here? The one of the electron from this is shifted to the excited state. So what is happening in this case? Which is the HOMO? This is the HOMO and this is the LUMO. Okay, in this HOMO, how the orbital will be? See, this is the 4 carbon atoms. 1, 2, 3, 4 carbon atoms. The fourth carbon atom you see here, they both are in this like this. On photochemical reaction, the orbitals will be in the both are in the same phase. But before that, before photochemical reaction, before the thermal condition, what will be the reaction? See, these these four these orbitals are the different blue and red and blue, red and blue, like this and this carbon and the atoms are looking like this. If this is the case on thermal condition, what we need to do? We need to do the symmetry, that is clockwise and anti-clockwise rotation, and we need to get the symmetry overlapping. If this type of rotation is called, if the both these are under clockwise direction, this is also clockwise, this is also clockwise, if this type of rotation is called conrotation. If in this case you see here one is clockwise, another one is in anti-clockwise, okay, then only you will get the symmetry overlap. This blue and this blue will get overlap. So this will be in a clockwise and this will be in the anti-clockwise. So this we call it as this rotation. Because of that only we are doing the this rotations and all. Okay, let us see the 5 hexatriene. In this case 6 electrons are there. See, 2, 4, 6 electrons are there. 6 carbon atoms. So 6 levels are there. And as I said earlier, the first level is always overlapped completely, same phase. And in the second phase 1 node, third phase 2 node, fourth phase 3 node, fifth phase 4 node, sixth phase 5 node. So one less node will be there according to the levels. Okay, see, the first 3 are bonding molecular orbital and the next 3 are anti-bonding molecular orbital. How many electrons? 6 electrons. So 2, 4, 6 electrons is there. This is the highly occupied molecular orbital, HOMO. This is lowest unoccupied molecular orbital. So after the photochemical reaction, one electron will excite to the excited state. This is the HOMO and that is the LUMO in this hexatriene. Okay, this is the 3 double bonds are there. So you need to keep then how many double bonds are there. That according to that, this lobe will get changed. See, in this case the lobe will be, both will be in the same phase. Okay, and thermal condition it will be in the same phase, and the photochemical condition this will be in the different phase. You can see that in the last video, the last slide. Okay, let's move on to the next one. Why you come to know why we have to do this rotation and all. According to this only, the Woodward created a rule that is called the Woodward-Hoffmann rule for electrocyclic reactions. What is that? On thermal condition, we need to see the two things: number of double bonds, one whether it is an even number of double bonds or the odd number of double bonds, that is pi bonds or double bonds. If it is a 2 double bond is there, that is even number. 2, 4, 6 and all even number, and it is 1, 3 means that is not odd number. If it is an even number of double bond, we need to do the conrotation. Why? The phase will be in the opposite phase. You no need to remember this. You no need to remember. That's for understanding. I mentioned over here that just even conrotation that you need to keep it in your mind. Why is it so? I'll just given in this. Okay. Opposite phase, so our phases are opposite means we need to do the conrotation, then only you will get the symmetry overlap. And in the odd number of double bonds, we need to do the disrotation. Disrotation means one will be in a clockwise, another one will be in the anti-clockwise. One will be in a clockwise, another one will be anti-clockwise, then only you will get the same or symmetry overlap. That is the same phase. If it is the same phase, we need to do anti-clockwise direction, that is anti-clockwise, one is clockwise, another one is anti-clockwise. This rotation we need to do. If you remember this is sufficient. You can do the photochemical reaction also. Just opposite to that is photochemical. The even is con means for photochemical even is disrotatory. For thermal odd is disrotatory means For photochemical, odd is conrotatory. So just opposite to that, these two. Okay, if you remember the even con, odd disrotation means here even this odd conrotation. That is easy to remember. And the next we will see the conditions how it is happening. See, in this is the 2 pi bonds are there. So it is an even number of pi bond. Even number of pi bond on thermal, it is a conrotation. Because it is a conrotation, then only we will get a symmetry overlap. Okay, and the odd in the thermal condition, if it is an odd number of the same phase will be there. What is happening in the odd disrotation we have to do, then only we will get the symmetry overlap. So according to that, this CH3 will change. This CH3 will go top and this CH3 will go down, and it is forming as a trans product. And in this case, if it is a 3 double bonds are there, in this case this rotation will happen. In this CH3, both the CH3 will go to this way. One is clockwise and another one is anti-clockwise. So what will happen? Both the CH3 will come down, and this is called as a cis product. We will get the cis product. And in the photochemical condition, if the double bonds are two double bonds, that is even number of double bonds in a photochemical condition, disrotation will take place because of the same phase. Okay, on that condition, if disrotation means one is clockwise, another one is anti-clockwise, so both the CH3 will go up. So this is a cis product. And in this case of a 3 double bonds, if it is a different phase, and we have to do the conrotation, and we will get symmetry overlap, and both the CH3, this will go here and this will go here, and both the CH3 will be in opposite side. The CH3 will come here and this CH3 will go there. Then only this overlap will take place. Because of this overlap, this CH3 will go to the opposite place. Then we get the trans product. This we have to see. Okay, thanks for watching. Subscribe my channel and click the bell button so that we will get the upcoming videos and like the videos and share to your friends.